Hi, I'm Carl, and in this video we're going to have a look at questions 36 to 38 of section 3 of the blue booklet. So this is a question about indicators and their pKa's. So we're told in question 36 that we have 3 test tubes, each with the same colourless solution in, and it has an unknown pH. It says when thymolphthalein is added to the first test tube, it's colourless. When alpha-naphthophthalein is added to the second, it is blue. If thymol blue is added, what would the colour be? Okay, so we're given quite a lot of information here. And so let's have a look at this first one. Because it remained colourless, we know that it's going to be in its acidic form in this solution. And if it's in its acidic form, that means that the pH of the unknown solution is going to be more acidic than the pKa, meaning that it's going to have a pH which is less than 10. So that's what the first one tells us. And then the second one says that it turns blue, and that's this one here. Which means it's going to be in its basic form, meaning that the pH of the colourless solution is going to be greater than the pKa here. So we know the pH is going to be greater than 8. So that gives us a range of 8 to 10. So then if we were to add thymol blue, what would the colour be closest to? So we're going to be looking at this pKa value now. What side of that is it going to be on? And we're told actually right above the notes that if there is a certain range of concentrations for the ratio between the indicator and the protonated and deprotonated form, then the colour observed will be a mixture of the two colours. So I want to explain why that would be here. So we've got a pH range of 8 to 10, so that's a pH range of 2. And remember, pH is a log scale in terms of a factor of 10, right? So it's going to be a log 10 scale. If we were to move from, and we're given this expression here, what these two values are is 1 times 10 to the 1, moving down to 1 times 10 to the minus 1. On a log scale, this is moving down 2 steps. And we're told when this, this is going to be negative 1. On a log scale, we're moving down 2 steps, which is going to be the equivalent for pH of moving in a range of 2. Meaning that if the range is less than 2, then you're going to end up with a mixture of these two colours. And because the pKa is right in the middle of this range of 2 that we're looking at, it's going to be a mixture of the yellow and blue. And we're told that that's going to give us green in this case. So we know the answer for 36 is going to be D. It's going to be green. It's just looking at the range of values there. 37 then says the range of pH values over which any of the indicators will completely change colour is what? Well, we've already sort of answered that. It's going to be a range of 2 because within this range you're going to end up with a mix of the two colours, but outside of this range you're going to end up with a complete colour change, so you're going to be able to tell them apart. So we've already sort of answered that question. It's going to be a range of 2, which is answer C. And then question 38 was a little bit more complicated. It says that we have a pH value of 7.1 in a particular solution. And I'm just going to draw a line here. We've got 2 indicators, the bromothymol blue, which has a pK of 6.8. And we've also got neutral red, which has got a pK of 7.4. So the pK essentially is going to be the pH at which there is going to be complete equilibrium, where there's going to be an equal concentration of both forms, the deprotonated and the protonated form of each indicator. So let's draw out first the equation for the dissociation of this. So this is the protonated form, and it's going to be in equilibrium with hydrogen ions plus the deprotonated form. And I'm gonna draw this out again so we can have some more room. But really the pH here of the solution can tell us a little bit about what will happen to this equilibrium, and comparing that to the pK will give us our answer here. So we have this equilibrium here, and the pK is essentially, how I think of it, is the pH that the substance wants to be at. So if it's in a solution at 7.1 and it wants to be at 6.8, what does it need to do in order to reduce the pH? So of course that's going to be adding more hydrogen ions. So the position of equilibrium is going to move in this direction, which means that the concentration of the stuff on the right hand side is going to be greater than the stuff on the left hand side. So on the right hand side we have the deprotonated form, and so we know the concentration of that is going to be greater than the concentration of the protonated form. So we can say now that N is going to be greater than M. And what about on the other side? Well, we have the same equilibrium that's happening here, but the difference now is a different pKa. So at this pH, it wants to be raising the pH. So it wants to be at 7.4, but it's at 7.1 at the minute. So it wants to reduce the number of hydrogen ions in order to increase the pH. So the position of equilibrium is going to move in this direction to mop up some of those hydrogen ions and try and get the pH to come to 7.4. So what does that tell us then? We know that the stuff on the left hand side is going to be greater in concentration than the stuff on the right hand side, meaning that there's going to be more of this protonated form. So R is going to be greater than S. So that's a pretty useful expression. It already sort of points us towards an answer, which would be answer D, but I want to explain where those equal signs come from. So for every hydrogen ion that one produces that the other one is mopping up, they're going to be equal. So this is producing more hydrogen ions and this is absorbing them. And that's what's keeping this pH constant. It's really just moving hydrogen ions from bromothymol blue onto neutral red. And that means that there's this one-to-one relationship between the two. So for every undissociated bromothymol blue that dissociates into this hydrogen and the deprotonated form, that hydrogen ion will go on to attach to a neutral red deprotonated form. So that's why we have these sort of equal signs, because every time we have this protonated form of bromothymol blue, which is M, that's going to be equal to the amount of deprotonated neutral reds, because the hydrogen ions are being swapped between them. So we can say that M is going to be equal to S. And if we know M is equal to S, and we know S is going to be less than R, then we know R is going to be equal to N, because we have this one-to-one relationship between the two. That gives us our answer D. So the answer for this one is going to be D in that case. So that was questions 36 to 38. I hope that helped.